specifics for the lightning one?
So the lightning is 1 kilometer away from the house. The lightning channel rises linearly to a peak level of 50 kiloamps in 1 microsecond, and then decays linearly to 0 at 10 microseconds.
10 microseconds, and this is 5 or 1?
It says it's in 1.
1 microsecond. Well, this isn't drawn to scale, but you get the idea. It goes out to 0 to 10.
It says also assume that the house power wiring has the 2 wires routed around the floor. Determine the induced voltage of the power input.
You got to see the picture of
Yeah.
Oh, here you go. Oh, yeah, this is, give me just a simple, and they want this induced voltage,
Yep.
the EMF. And what's the dimensions here?
The width is 90 meters and the height
90 meters?
Yep.
Okay. And that,
Is 3 meters.
call that W, call that H equal 3 meters?
Yep.
That's a weird dimension.
Mm-hmm.
All right. Well, this is the classic. Is the lightning current assumed infinitely long?
Yeah, it says a very long.
Yeah.
All right. Well, this is the standard one where we could get the mutual inductance and just use M times di dt for the induced voltage there, because mutual times time varying current, it gives you the induced voltage. But we can go through it from scratch too. So if this is an infinite wire, if I'm a distance rho away, I know the B field into the page, if this is the current I of t, is simply going to be B is equal to I of t times mu over 2 pi rho, and it's in the A phi direction, where A phi would be into the board. Do we all agree on that, class? Now, the next thing you gotta do is calculate the magnetic flux through this loop, and that would be a double integral of B, which would be mu times I of t divided by 2 pi rho, and the A phi direction dotted with dz d rho A phi, that's the differential surface. And here z would go from 0 to 3. Do y'all agree with that, class? And where would rho go from? Now take a look at that. Rho, it's a radial distance. Where does it go from?
1 kilometer.
Well, it starts at 1K, very good. To 1K plus 90 meters, right? If that's the case, correct? So that means that's going to be the magnetic flux. And then before I even do this integration, I'm going to make this case. I know that the induced EMF, and in this case it would be sensed this way, going around the loop counterclockwise, is minus d dt of this. That would be VEMF. And that's sensed, wait a second, yeah, that's sensed in the counterclockwise. Let me do it this way, and I'll show you what I'm talking about. Here, this is normally plus to minus, right? And this is the voltage where that's plus, that's minus, that would be sensed. So if you pull it around to the other side, then the plus would be down here and the minus here. But I'm going to just leave it right here, okay? So for this one, when I take the time derivative of this, I didn't do it yet, but it would really be di dt of t dt would have the time derivative. Do you all agree with that? I just pulled the time derivative inside there. Everybody? Okay? Now, here, and there's a minus sign too. Here I can say that's minus mu, I can take that out in the front, times di dt over 2 pi, right? And then I'll do my A phi dot A phi is 1. When I integrate dz from 0 to 3, I simply get 3, right? And when I integrate d rho from 1 kilometer plus 90, I'll get a natural log of rho, or natural log of, really that's going to be 1090 divided by 1000 in terms of kilometers. And that would be VEMF. Now here, you have to take a look at everything but di dt, I'll leave the minus there, and see what it comes out to. So if you take 3 times the natural log of 1090 over 1000, that's just about the log of 0. I mean the log of 1, pardon me. It's small. Divided by 2 pi and multiplied by mu naught, what do you get? So mu naught's 4 pi times 10 to the minus 7th divided by 2 pi would be 2 times 10 to the minus 7th times 3, which would be 6 times 10 to the minus 7, times the natural log of 1090 over 1000. What do you get for that? Anyone? No. Got it, Ivan? It's mu over 2 pi, just use mu naught 2 pi times 3 times the natural log of that. Did you get it? Duncan? No. Anyone? That's what I'm looking for. 2 times 10 to the minus 7 times 3, which is 6 times 10 to the minus 7 times the log of that. Anyone?
I got 5.2 times 10 to the negative 9.
Okay. Say that again.
5.2 times 10 to the negative 9.
Anybody confirm that? I'm just looking for the inductance. This is the mutual inductance.
I've got that to the negative 8.
Is it 8 or 9?
Not negative 8.
Yeah, negative 9.
All right. Minus 8, that's fine. Now, when we look at this, that's I of t, but what we really need is di dt, right? Versus time. This is 1 microsecond. So if it goes from 0 to 50 kiloamps in 1 microsecond, the actual di dt would have a value here of 50 times 10 to the minus, or 50 times 10 to the third over 10 to the minus 6. And that's going to be 5 times 10 to the 10th, isn't it? If you look at that. I'm sorry. Yeah, that's right, isn't it? 10 to the minus 6 upstairs, 10 to the 6th, 10 to the 9th, 10 to the 10th. 5 times 10 to the 10th. That's where it's going to be at out to 1 microsecond, and then it's going to invert the polarity, and it's going to go down because now the slope's going to be, this is negative, and it goes from 50 kiloamps to 0 in 9 microseconds. So this is going to be minus 50 times 10 to the third over 9 times 10 to the minus 6. So what is that going to be? That's really 5. This is going to be minus 5 times, and that's going to be 5 over 9, minus 5 nines times 10 to the 10th, right? Correct, class? All right, now that's the di dt out to 10 microseconds. So you can say that VEMF, therefore, the induced voltage. Now, the thing about this is minus the IDT, and I've got the polarity such that that's positive, that's minus, right? If I got rid of this minus sign and just switch the polarity, then this would be plus and this would be minus, correct? Now just take that all the way around. You see how on this side, if I push that around, it would be plus minus. Do you all see that? All right. Now that's actually what I saw, that's the picture.
Yeah, that's how it is.
All right, you can see that I've gotten rid of the polarity and stuff, so this is going to be equal 5 times 10 to the minus 8 times 5 times 10 to the 10th would be the voltage here. And what does that come out to be? What is that, 25 just about times 10 to the 2, so it's about 500. Could you go ahead and multiply 5.2 times 10 to the minus 8 times 5 times 10 to the 10th? Just give it. It's about 25 times 10. It's about 500, but I think. Anybody?
2585.
You're right. Okay. 2585, and that's from 0 to 1 microsecond, and then VEMF will be equal to, and now take this same number times this. volts? Anybody?
So it sounds right, yeah.
It's gonna be roughly 1/9 of that, I think, in magnitude, but I'm not absolutely certain. What'd you get?
Negative 287.
Okay. Minus 287. And that's from 1 to 9 microseconds. Or 10 microseconds, sorry. Is that what you asked?
And there's no answer, is there?
Yeah, there is.
Yeah, that's it.
All right. This is simple. This is a classic problem, by the way. I want to tell you. I want you to look at these voltages. By the way, these timescales are right. Rise time about 1 microsecond, peak current about 20 to 50 kiloamps, and then decay time about 10. Actually goes longer than 10, but what it does is one of these things. The real lightning waveform, it looks more like this. It's a double exponential. It comes up, crests, and then it'll start coming down, and then there'll be this long, long duration tail on it, but you can sort of asymptotically click it down there. And that's about the kind of voltages you can expect to induce on, this is a simple loop on a house that they try to estimate. That's significant. But notice the duration. These things are less than 10 microseconds in terms of the entire event. And one other thing you get on real house wiring, because this is a mutual inductance with this thing, and this is actually coupled to other parts of the house wiring. So if you looked at the voltage you'd get in the house wiring, you'd see this. You'd see a real spike like this, and then it would ring and then go down and something like this. And you'd see a lot of ringing. You won't see just a up, down kind of thing. Remember that. You get all sorts of ringing. Really, this type of problem, when lightning's distant like that and it's induced EMF, your house is set up for that. It's got all sorts of things that deal with that kind of problem, filters and stuff like that. But the problem, the real problem, is if lightning hits a cable connected to your house. Has anybody ever lost a TV or a stereo or anything like that when lightning hit the actual, this has happened to people I know, happened to my wife used to live at, and years and years and years ago when she was in school, she lived at the Reserve. This is a long, long time ago. And they had they had this cable coming right to your place, and she had an old CRT, not an LCD screen, a CRT screen. And this was, I think, during the 2011 tornadoes that came through here in March or April, and I think it was April. And they had tons of lightning hitting there, and her TV got knocked out by one of the things they were watching, then thing just, the whole flyback transformer, I think, not flyback, but the input transformer got blown apart. I didn't see the TV, but I know it didn't work after that, and I did suggest you try to fix it. Anything else?
On that problem, for the rest of the homework, you assume that you don't need to know where the current is flowing to create the B field?
If they give you the B field, you don't care what created it. Once you have the B field, that's all you need, right?
But if you're finding differential surface, you put the 0 where the current is flowing?
Well, which problem are you talking about?
The one we just did.
Well, the current was 1 kilometer away, right? So
Yeah.
the differential surface is just going to be a differential inside that loop. Hold on for what's that? Okay, I'll be right back.
I think we figured it out, and that I didn't realize that it wasn't a constant B field like in the other problems.
No, as a matter of fact, it's not only not constant, but it's time varying.
Well, yeah.
And that the reason, because the B field's time varying, it makes it something where you almost need to do the integral of D dot D or B dot DS integrated over there, because if that loop area is changing too, then the problem, you can't just use mutual inductance. Let me explain one other thing. You were taught a long time ago that if you have an inductor L that the voltage across that inductor, VL, was equal to L di dt, right? And that would be a current I going into it. Do y'all remember that? Well, that's partially true. That's true if the inductance doesn't vary with time. But if it did, VL would actually be equal to d dt of the quantity L times I of t, which would be equal to I of t times dL dt plus L times di dt. Now here's why that's important. The only application I've seen this used for myself was if they want to get an extremely large voltage generated and they have limited resources. So what they'll do is they'll take a standard battery. Well, this ain't a standard battery. Think of like several car batteries in parallel. All right, so you can get of the order of hundreds of amps of current. And this current is going to flow through an inductor like so and down. And the inductor here, all right, right at the edge, let's see here. Yeah, the edge right here and here, they'll pull a voltage off of it. Now, they first allow the current to go to I max, and it could be 200 or 300 amps, maybe up to 1,000 amps, all right? And then what they do, they have this thing packed full of a high explosive, and they set it off. And they also instantly like blow out this line and this line. Now, what happens is now you get a time rate of change of the inductance, but the current's still flowing. So in the initial picoseconds, all of a sudden the voltage here can get to be like, if the current's a couple hundred amps, but this di dt is 10 orders of magnitude, or 12 orders of magnitude in terms of the actual value compared to this would be dominant, and they can get voltages of up to 1 billion volts, all right? Only for an instant here, but what they do is then they drive things that are, I call them special antennas, but they're things that can take that and launch a waveform quickly, convert the electrical current or electrical voltage energy to photons, and that's something called an electromagnetic pulse flare. That's the term I use for it. You've heard of EMP, right? You know that for computers, things made with microelectronic circuitry where you have gates of transistors, or you have the p-n junctions that the minute you short across those things, like a capacitor, you destroy the operation of the circuit. And that's how come when a nuclear weapon goes off, the very fast rise time will devastate these kind of things, computers, if they're not shielded. And they'll shut off your car and all that. However, nuclear weapons aren't usually available for things like that. If you want to disrupt electronics, they can do it with this. This will create, they can literally get the same very high intensity, short duration electromagnetic pulse from something like this, and they can disrupt electronics. It's an EMP flare. And that's something you're not going to hear about in the news. Matter of fact, nobody will probably be allowed to write about that. But I just want to let you know it's due to this effect, the time change of the inductance. And you can do all sorts, there's probably other applications, but you gotta understand it's a destructive mechanism. It's a one-shot, it only works once. All right, it's not something that can be done over and over again in a factory setting if you need that. But it fits well here, because with lightning too, another thing about lightning, a lot of times, when lightning's hitting, oftentimes it's destructive, and the actual, quote, mutual inductance that's coupled to it, in some cases self-inductance, is going to be destroyed, which means it's going to be changing, time rate of change, and you can get all sorts of incredible voltages developed over things when lightning hits. If you ever get a chance, you want to see something, YouTube probably has this. Go on YouTube and look for lightning impacting house/buildings, and put super bolt, not just put bolt, because these are lightning currents that are up to 270 kiloamps peak, and it's amazing. I was fishing one time years ago. This is my area, my doctoral area was lightning, and I did a lot of research and published a lot of stuff related to lightning, and really the electromagnetic transients related to lightning. And underground currents induced by some things like this. Well, I was fishing down, if you know where Phoenix City is, there used to, before they have a river walk. Does anybody know what I'm talking about down? Before the river walk was there was an old mill dam. It was just a spillway. because there was a mill there and the water used to spill over the top. They didn't have they didn't have turbines running or anything like that. Well, on the other side of that dam was an old mill, and the mill had like a barbed wire fence around it, if you know what I mean, to try to prevent people from rhinos and stuff from getting in there. So I'm fishing, and it's raining, we're catching a lot of fish, and I'm on the shore, and lightning's hitting around here. Doggone it, it hit the mill area at the top, but I watched sparks fly all the way down there where it was inducing a large potential, and it was literally causing sparking from the top barbed wire all the way down to like the base of that. And it was amazing how far reaching the effects were. And if I was down there by that fence, I would have probably been shocked fairly heavily too. So lightning's like that. You don't want to be near it when it strikes, trust me. Has anybody been near a lightning bolt when it hit very close? No?
I was one time at a camping trip.
Did your ears ring? Was it that loud?
Yeah.
Okay, that's when you know you're in danger. If your ears ring. And it is scary.
I felt in danger.
Any other questions about the homework? I'm sorry I walked out of here for this thing. I wanted to get this because I'm gonna do something.
The second one, which was a,
Let me just take a peek. It's got like concentrics.
yeah,
All right, the outer one, I'll put the resistors in a second, but is this a closed loop or not?
no, it's not.
And then they have an inner one like this.
Yes.
All right, now where are the resistors?
The resistors are on the
Here?
inner loop, yeah, one there,
And that's it?
yes.
Okay, now give me a value R,
100, and then 50.
50, okay. And what's the dimension here?
That's 10 centimeters.
And this?
The full length of it's 30 centimeters.
So just call this 10 and 10 cm, okay? I'm assuming it's in the middle. And they have a gap here?
Yes.
They want this voltage?
Mhm.
And what's this dimension?
1 meter.
1 meter, okay. And what's the B field? Is it into or coming out of?
Coming out of,
Is it homogeneous?
yes.
Okay, and what's the B field value?
It's into
It's what?
the field, or into the board.
Oh, it's into the board,
Yeah.
sorry. Okay, and what's the value?
2T milliwebers per meter.
2T milliwebers per meter squared, okay? And they want this voltage, right?
Mhm.
All right, now, remember, this is an open circuit, but this is a closed circuit, right here. And this is how you have to think about this. Now, when we look, I told you that what you could do is anytime you had these problems, and I'm gonna just come out here for a second, that if I had a loop with a resistor in it, and I wanted to know, and I had a B field, I'm gonna put the B field into the board, and I wanted to know, say, what the voltage or current was flowing on this. If I want I or V. Well, I'm just gonna say the loop has an area A. A would be W times H, call that H, call that W. Now, the way you go about this is first, do the problem the way I set it up originally. You assume that this thing doesn't have a resistor in there, get rid of the resistance, and assume it has a little break here, plus to minus. And that's the voltage you're gonna get first, that VEMF, all right? If you do it this way, you won't get confused. Now that voltage right there, I know VEMF, the way I've drawn it, is equal to minus the integral of B dot ds over the surface that's contained or in, where the loop's the perimeter of the surface. Understand, everyone? Well here, this is really, since the B field's a constant, well, I'll put it down. B field's into the board, and I'll give this some dimensions, call this X, Y, and Z. So the B field is actually into the board, which is gonna be minus, and I can just use that B, I'll just leave it B of T, and it's AX. That's the B field that's going into the board. The differential surface right here, ds, would be equal to whatever this coordinate is, which would be z, dz, dy, and it would be out of the board. Remember, with a differential surface, you grab the surface with your right hand, and your thumb points in the direction of the surface. Follow me on this one? So this is positive ax. So I have this, and then it's going to be dz, dy, ax. We don't care about this. We're integrating over the surface, and the B field's a constant. Now, ax dot ax is 1, but there's a minus sign there. And remember, there's another minus sign in front of that, so they cancel, is my point. Understand that, class? Remember, it's minus this. That means there had to be a minus there, and then the B field is into the board, so it is sensed minus. Follow me? Now, it's important the differential surface here, remember, it's out of the board. B field into the board. Well, the two minuses cancel, and then I get B field times area. So it's really going to be, and it's minus ddt of this. Minus ddt of this. I'm sorry, I didn't put that. Minus ddt of this. And that means it's going to be, since there's two minuses, they give a plus, and it's going to be plus the time rate of change of the B field times simply the area. And that's what this is going to be. Okay, follow me? So that means this voltage is positive, and it would be that value, correct, class? Now, I did this for a reason. I'm trying to move through this fairly quickly. Now, I ask myself, how would I put a source voltage in this loop to create this voltage in the gap? And I would have to put it in with the polarity plus to minus. Do you follow me? And that's what this is going to be. This source voltage here, my VEMF, is going to go in there. And this is now going to get shorted. And now I put my resistor in there, R. And now I can get anything I want. But you'll notice the current is being driven counterclockwise here. All right? And it is a function of the derivative, time derivative. For us, the time derivative is just going to be what? That was 2t milliweber, so it's just 2, right? That means if I look at these loops here, if you bear with me now, I can say I can leave that open, but I can say I can put in a voltage here, plus to minus, where that voltage is just going to be dB dt times the area, the outer area. So this voltage, and let's call it just V1, would be equal to dB dt times area 1, and area 1 will be the outer area of this thing, so that's going to be equal to, what is that? That's 30 centimeters times, is it 1 meter this width, or 1 centimeter?
1 meter.
All right, so it's 0.3 meters squared, right? 0.3 meters squared times the ddt, and that's going to be, really, I'll get rid of the units here. That's going to be equal to just 2 times 10 to the minus third. So that's the voltage V1. Do you all see what I'm doing here, class? Right? I'm taking the outer area times the ddt, correct? And I have to get the right polarity here for this pseudo source I'm putting in. Yes?
Are you gonna subtract the inner loops area?
I'm going to in a second, but first you have to see how this one works on the outer loop. Now in the inner loop, it's the same thing, right? And now I'm going to put a pseudo source on the inner loop right here. And I'll call this, I know the polarity is plus to minus, and I'll call this V2. And V2 will be the same dB dt, but now it's times A2. And A2 is going to be this dimension. By the way, what is the width of this thing?
50 centimeters.
50 centimeters. So it's a ½ meter. That means the area here, which I'm calling A2 would be equal to simply 50 or 0.5, right, times 0.1. And that's going to be 5 times 10 to the minus 2 meters squared. and it's times dBdt, so the actual voltage here, V2, I'll try to make this a little easier to understand. This V2 right here is going to be equal to 5 times 10 to the minus 2 times 2 times 10 to the minus 3, isn't it, class? It's dBdt, which is 2 times 10 to the minus 3 times the area of the second one. And what is that going to be? That's 10 to the minus 5, right? So it's 10 to the minus 4th, is that what you got? 10 to the minus 4th? So this voltage here is 10 to the minus 4th volts, and this voltage is what? It's going to be 6 times 10 to the minus 4th, isn't it? Correct, class? All right, now, here's how you do the problem. I want you to take a look at this next part. Let me erase, or let me do this right here and show you. Try to get it uncluttered a bit. I'm going to take out all the unnecessary stuff and reduce this to a circuits problem. So now I have this. I have plus to minus 10 to the minus 4th volts, and that's really 100 microvolts, right? Right here. And then I have a resistor here of 50 ohms, and I have another resistor here of 100 ohms, right? And then I have out here a source. The source is like this, plus the minus, and that's 600 microvolts, right? That's 600 microvolts. And now I want this voltage right here. The rest is inconsequential. This is plus to minus V, correct? And that's basically it, correct, class? I've taken away everything but the voltages and resistances. Now, when you look at this, if you start at the negative terminal here, and you work around, you get to a point where there is a voltage change here, a voltage drop or gain, right? What is that voltage going to be? You see how in this closed loop right here, we have 100 microvolts, right? And it's being divided between 50 and 100. So what would this voltage be here? It would be plus to minus, right? And it would be 100 over 150 times 100 microvolts. Do you agree with me there, class? That would be 66 microvolts, isn't it, class? So this would be 66.6 microvolts. Agreed? Okay? All right, now if that's the case, what's the voltage from here to here? That voltage would be equal to, is this an increase or decrease?
Decrease.
What?
Decrease.
Decrease, yeah. It's minus 66.6 microvolts, right? And this would be an increase of plus 600 microvolts. So what does that come out to be? 533 microvolts, is that right? 533 microvolts, approximately. Is that his answer? You all see how I did it? And I put in pseudo sources for that. Remember, that's the easy way to do it. When you do these problems, after you do a bunch of them, you don't need to. Just start with a square loop, put in the B field in the right direction, and you got a square loop like this, then break it right here, put plus to minus VEMF, and say that VEMF is equal to minus ddt of the integral of B dot ds over the surface of this loop. Now once you get that, then you put in a pseudo source. What source will cause this voltage to be developed? And it's going to be something where this is plus and this is minus. And then you do that, and then you do whatever else you want. You put in resistors. Okay? Yeah.
I subtracted the area of the smaller loop from the larger loop, but I still got the same answer.
Yeah, that's you're trying to see that probably more coincidence than actual, because it's always the integral of B dot ds, right? Over the surface, right? Well, we have two loops that are in the same, one's inside the other, right? Here's the problem with the areas. What if this 50 is over here and this 100 is over here? Then there's a different voltage percentage that gets taken, or different voltages subtracted from that outer loop. Do you follow?
Yeah.
So if that's just a straight wire there, none of this voltage in here would have any effect on the total voltage. Follow me on that? That's how come you gotta be careful to make sure you put in the pseudo sources and the resistors in the right place for each loop. Okay. I'm not sure if yours is coincidental, but it sounds like it. Anything else? I give you a bunch of those problems, and some of them were pretty good. I thought they were pretty good, at least.
I've got another one.
Which one?
So, it's the sliding bar,
Okay.
and you're supposed to determine the current
Mm-hmm.
if the magnetic field is a constant 10 milliwebers per meter squared,
Mm-hmm.
and the velocity is 100 cosine 10t meters per second.
Now, this is one you can do a couple ways, but I'll show you the easy way to do it. They have a resistor here, don't they?
Yeah.
And we'll just leave it as R. And then they say they have a long rail, and they have some bar here. And the bar's velocity is given, is that it?
Yes, 100 cosine of 10t
Cosine of 10t meters
meters
per
per second.
Okay, and what's the width?
I don't think there is one.
50 centimeters.
50 centimeters?
Oh, yeah.
Okay. They have to give you a width. Now this is conducting bar. And the B field's constant? Is it into or out of the board?
Into the board.
Okay, so we have a B field into the board. And that B field is equal to 10, did you say?
Yes, 10 milliwebers
10 milliwebers
per meter squared.
per meter squared. All right. Now, here's the deal. If this B field here was time varying, all right? If it's time varying, then you would have to do the problem by first calculating the total integral of B dot ds inside that loop and then taking a time derivative. So in general, if the B field is time varying in here, then the steps you have to take is you find first the induced VEMF by taking minus d dt, the integral of B dot ds. So if it's time varying in here, B dot, even if this thing wasn't moving, if it's time varying, then you're gonna have B dot ds and you're gonna have a derivative and you're gonna get a value of voltage, and that would be for the open circuit voltage there. Do you follow me on this, class? That's one thing. But if it's not time varying, and this isn't, then this integration for the bar being held constant will be zero at a constant. However, the bar is moving, right? Now this is the best way to do it. Since the bar is moving, the bar is the only thing that is going to get an induced voltage across it. All these rails here really are nothing. Nothing's going to happen because there's no time varying B field there. Follow me? So this is one of those things, we just look at the rail and find the voltage across it. And remember, the way to get the direction of the E field and thereby the polarity of the voltage is V, right? Cross B is the direction of the E field, right? So I can say that the E field induced here, caused by the motion, is equal to V cross B. And since V is this, and B is that, it's going to be 10 times 100, or well, really this is 10 to the minus 2 times 10, it would be just 1, right? Because this is 10 milliwebers, 10 times 10 to the minus 3 is 10 to the minus 2, times 10 to the 2 is just 1, correct? It's 1 cosine of 10t, so this E field would be just cosine of 10t, and that would be now volts per meter, because I took V cross B, and it's in this direction, right? Now remember, this looks like this is like internal to a battery. It's shoving positive charge here, and it's causing negative charge to be associated with that. This is like an internal force here. Follow me, class? That means this voltage from top to bottom here, the voltage on the bar, polarity plus to minus would be equal to what? It's going to be this E field, right? Dotted with DL and integrated from here to here. You all see the DL is in the vertical direction on that bar class, right? It's in the same direction as the E field. So if we just take the length of the bar times the E field, we'll get the voltage. Do you all agree? And the length is half a meter, so it's really going to be 1/2. It's this times 50 centimeters. It's 1/2 cosine of 10t. Do you all agree with me? Because that's the velocity of the bar, correct? It's 100 cosine 10t meters per second. Correct, class? Now that's the voltage here. It's 1/2 cosine of 10t volts. So how much current is going to flow in here? Well, this I of t will simply be equal to that voltage, V bar, right, divided by R. And that's going to be 1/2 cosine of 10t divided by, what's R?
100 ohms.
Divided by 100, so it's 1/200 cosine of 10t. Is that what he has?
Yeah. He's got 5 cosine 10t.
What's the units?
Millions.
That's right. All right, that's how you do that problem. Everybody follow me on that, class? Now, one thing on tests, hint, hint, I can make that a time varying E field. And then you have to do the integral of B dot ds, which means you have to find out this distance. Now, if that's the velocity, you have to, it has to be said where the starting point is. If the thing is right here, right, and it's moving back and forth, then you can get the position by integrating velocity dt to get the position x of t, correct, class? But remember, these problems, the key thing is whenever you're uncertain about if you can just use this, see if there's a time varying B field. If there is, then you right away go to the integral of B dot ds over the surface contained within, contained within the perimeter of the bar and track. There's a classic problem in Dr. Wentworth's book also that does this. He'll take a bar and he'll have this. He'll have a resistor R here, and then he'll have a width here, W. But he'll have the rails flaring like this, and he'll assume an infinitely long rail moving in this direction. All right, now when you look at the integral of B dot ds, you've got to calculate that area first, right? Times the B field. Well, that area is what? If this is velocity V, then you have to find out how far out you are this way first, which would be the integral of V times dt, correct, class? And then you have to find out how much area it is. So if you know the slope of this and slope of this, you can go ahead and say that's a triangle, and you can get the areas there. But the problems get more and more complicated by either flaring the rails, changing the time varying B field, or making the velocity be in this case it's a function of time. So they can get different levels of complexity. Any other questions about the homework? Did you try these problems, guys? Did you get most of them or not? You got most of them? Good.
I did. I got the right answer, but I think I did them the wrong way. So
That's. See, I wish I had that happen to me when I picked stocks. I picked them for the wrong reason, but it turns out they all went up. All right. Next, this is going into the last stuff we're going to cover. I am going to do the magnetic force on a bar, the lifting power of that, but not right now. Today I had a special thing I wanted to cover, and that is going to be actually, this is going to be what's called the wave equation. We're going to develop an equation that describes electromagnetic energy and really propagation. So it all starts with Maxwell's equations. And the first of the two is curl of H is equal to really J plus the partial with respect to T of D. And the second is curl of E is equal to minus dB dt. That's the second one. And the coupling is D is equal to epsilon E. It's also J is equal to sigma E. And it's also B is equal to mu H. These you have to know very well. You have to know those very well, and you have to know these very well, because you're going to see these over and over and over and over again. This is Michael Faraday's law of induction is here. This is Ampere's circular, they call it the circular law, but it's Ampere's law, all right? And these are both point forms or differential forms. Now, when we take a look at these, normally the first thing that's done when we're doing wave, any type of work where we want to take a look at the effects of propagating electromagnetic energy, we do one thing. We go into the phasor domain, and we'll also eliminate some of the confusion by only solving for two variables, which will be H and E. So I have to first say this, and I always do this to my classes, and I did it to this class already. Normally when you see a circuits problem, if you have plus or minus, say, V0 cosine of 377t, right? Oh, well, let me do it this way. I want to put the problem, this is the kind of problem they'll give you when you go for a job interview sometimes. A very simple one. They'll put a voltage here and they'll just say like it's 10 times cosine of 20 pi t plus 30 degrees. And then they're going to have a resistance, say 10 ohms, and they'll have an inductor here, they call that L equal 30 millihenry, and they'll want the voltage here. When you go for job interviews, they always check, not always, but most of the time, if you're going for, if you've got a bachelor's, not master's degree, bachelor's degree in something, in electrical and computer engineering or wireless engineering, or in something like that, and you go to Intel, for instance. Then they give you a bunch of simple problems to make sure you're not just one of these guys that's like, knows how to copy and use the cheat on scan sheets and get high grades and don't know anything. And this happens, they get rid of people like that. And they'll say, I want to know what V of t is in the time domain and the output across this inductor. Now you're electrical engineers, you're going to do this a little different than physicists. So how would you do that? Well, you would do something that's very common. You did it in Dave Irwin's class all the time. You take it and put it into the phasor domain, right? You don't solve this in terms of a differential equations problem like physicists would. You would say this is equivalent to 10 at an angle of 30 degrees volts, right? And then instead of having this inductance, you would put down impedance here, which would be J omega, and omega would be what? The coefficient of t inside the cosine, right? So this would be equal to 30 supposedly millihenries, so it would be 30 times 10 to the minus 3, right? Times 20 pi ohms, right? I don't know what that is, but it's a value, correct? Just call this thing call it JXL. So it's the impedance of that inductor. Then you would say that you can use voltage division to get this value of voltage right here, and this would now be V tilde out, right? It would be a phasor out. And the output voltage, V out tilde, would be equal to the input voltage, 10 at an angle e to the j 30 degrees, right? And then it would be times this, which I call JXL over JXL plus 10. And that would be the output voltage in the phasor domain. Do you all agree with that? Do you all agree that has a magnitude and an angle, right? So it's going to be some magnitude V out, and it's going to be at some angle, theta. I'll call it theta V out, right there. Now that's still a phasor quantity. It's magnitude and angle, correct? How do you get it back into the time domain? This really can be written as V naught e to the j, and I'll just call it phase angle V. Well, to get back into the time domain, to get V out of t, now you take the real part of the voltage, really V phasor, V out phasor times e to the j omega t, and that means it's the real part of V phasor, some V naught, e to the j theta v times e to the j omega t. And that means it's the real part of v naught e to the j omega t plus theta v, right, the phasor form. Are you with me, class? I'm doing this one time because I know there are students that don't know how to do this, that sit in my classes all the time, and they don't even ask about it. Now this, e to the j omega t plus phase angle, is really cosine of theta plus j sine theta, isn't it? What rule is this, or what law, or expansion? It's an identity. It's Euler's identity, right? And this is there's three of them. This is what e to the j theta is. There's one for cosine, one for sine. You have to know those very well. So when I do this, and I expand this, I get cosine of omega t plus theta v plus j sine of omega t plus theta v, right? Well, the real part of that is, the real part is only the cosine. So that means this becomes simply v naught times cosine of omega t plus theta v. I did that whole thing to show you how you've been using phasors and how you would solve a time domain circuits problem with them if it was a constant frequency. That's the key. You can use phasors with constant frequency. Well, we're going to do the same thing with these equations. We're going to use phasor analysis. We're not going to write a bunch of time domain differential equations, even though we could. And I've done that before. Physicists do it all the time. They don't lend themselves to a solution, an easy solution usually. That's why it's to be avoided most of the time. So now coming back to these equations, I'll take you into my world. Solving these things numerically is what I do a lot of, at least in the past. Now I'm going to take these two and I'm going to find one equation with one unknown. First, I didn't say this, but you remember anytime you have a time derivative in the time domain, it boils down to j omega in the phasor domain. Do y'all remember that, class? I can prove that, but do y'all remember this, class? If you're at a constant frequency or phasor domain. So first thing I'm going to do is take the top equation, curl of h, and I'm going to replace j with sigma e, and I replace d with epsilon e, and that time derivative with j omega. So the top equation becomes curl of h is equal to sigma e plus, and then this would be j omega epsilon times e, because d is epsilon e, and the time derivative is replaced with j omega. Do you all see this, class? All right. Now, what I'm going to do is group the sigma and j omega epsilon separately. So I have curl of h is equal to sigma plus j omega epsilon times e. And that's taking this equation and substituting in j is sigma e, d is epsilon e, and replacing the time derivative with j omega, thereby taking it into the phasor domain. All right? Now I'm going to work on the second one right here, curl of E. Curl of E will be equal to minus d dt of B, which is minus j omega, and then B will be replaced by mu epsilon. So it's minus j omega mu times h. I'm just taking Michael Faraday's law of induction and taking it into the phasor form. Now I have two equations. This equation, call this one, call this two. Two equations and two unknowns, E and H. I want one equation with one unknown. To get that, does anybody have an idea? Because I've done this before, back when we did transmission lines, but not with H and E, but with V and I. Do you remember? Anyone? There's one key thing. You're right. Take the curl, and if I want it in terms of E, I would take a curl here. So now I get curl of E. Took a curl of this side is equal to minus j omega mu times curl of H on that side. Correct? Now, you haven't had vector calculus, I don't believe. But this is one of the commonest identities. It's used all the time. a curl of a vector like that can be represented as the gradient of the divergence of that quantity minus the Laplacian of that quantity. So this is the gradient of the divergence of E minus del squared of E is equal to minus j omega mu. But what do you think I'm going to do with curl of H?
Well, substitute.
Look down there at 1, right? I can substitute the curl of H with this, and that means it's going to be sigma plus j omega epsilon times E. And now I have one equation with one unknown. That's equation 3. Everybody with me on this one? Now these del squareds and gradients and stuff, those are spatial derivative operators, but they are going to result in a vector. They will have a vector sense to them. All right, and E in general has a vector sense. They're not scalars, and that's important. But here's where we have to make some assumptions, or else we can't get anywhere. Because this equation by itself doesn't have a closed form solution in general. You have to, either you can numerically solve this with a computer, inside a certain region with specified sources and stuff, or you can try to reduce this to something where we can take a look at how the electric field would behave, say, if it only had one polarization, only say in one direction, it was propagating in only one direction, and it was a long way from the source, and that's what we're up to. We're also going to make a stipulation it's charge-free. So here's where the assumptions come in. We're going to assume rho v is 0. Now, if rho v is 0, the divergence of d is 0 as well, isn't it? Because div d is rho v. And if divergence of d is 0, well, d is equal to epsilon e, so that means divergence of e would also be 0. Correct, class? By the way, what law is this? Div d equals rho v. There's a word for it.
Gauss law?
Do you remember? Gauss's law, right? Gauss's law, you're used to seeing the integral of d dot ds over a closed surface is charged and enclosed. But this is the point form of Gauss's law. Divergence of d is rho v. And here I've made rho v 0. Now, I keep going on this one. And since that's the case here, I can get rid of this. Because if that's 0, the gradient of 0 is 0. Take a derivative of 0 is 0. So now I have this, right? And now here's where we do some things to make life easy for ourselves. First, we create something called a propagation constant. And we say we're going to say gamma is a propagation constant. It's equal to alpha plus j beta. And that's equal to the square root of j omega mu times sigma plus j omega epsilon. Now here's what I've done. I've taken this coefficient right there, well actually, and I've taken the square root of it. And I said that's alpha plus j beta, and this is called the propagation constant. If you'd like to, you can write that down. Propagation constant. Alpha is the loss, or really it's attenuation coefficient. And beta is the wave number. Wave number is in radians per meter. Alpha is in Napiers per meter. A Napier and a radian have the same units. You're gonna have to just accept that. If they didn't, you couldn't add these two up and get that. That's an R. Now, bear with me. The reason I did this is I'm going to take the minus the del squared of E to the other side. So I'm going to have del squared of E here. And then I've got minus, and this is really gamma squared. So it's that is minus gamma squared E equals 0. And this is a very famous equation. This is the Helmholtz equation. Or the wave equation. Actually, it's a form of wave equation. It's one of many. The way you tell the wave equation, if I wrote this in the time domain, it would have to do with the second order derivative of E with respect to t, second order derivative of E with respect to position. It's got, both are second order derivatives operating on time and space. That's called the wave equation. You'll see that in physics all the time. The fusion equation is first order in time, second order spatially. And I'm just going to leave that one alone for now, but that's how you know these two types of equations. If you've heard of the diffusion equation, I showed you that a while ago. This is the wave equation. Now, when we have this right here, we still haven't got down to a closed form solution or something that we understand. So what normally is done here is they're going to say that I'm going to be talking about something called a plane wave. So you got to write that down. Now, what is a plane wave? And I'll try to do my best to explain plane wave. Well, if you think about this, suppose I drop a stone in a puddle right here, and I allow the ripples to go out. You'll notice the ripples have really contours of equal altitude or equal potential, equal surface height, and they would form giant rings as the thing moved out, right? If you drop a pebble in water. Well, with electromagnetics, when you excite some charge and accelerate it, what happens is there's going to be electromagnetic energy that radiates, an E field that radiates. It's not anymore connected or tied to the actual charge creating it. And this is unlike the E field on a capacitor. If you charge a capacitor, there's an electrostatic field around the capacitor where all the electrostatic energy is stored. And when you put a resistor across the capacitor, it shorts all the charge on the plates through that resistor and brings the potential down to zero. And what happens is it takes the energy back out of the field and puts it into the resistor, the current going down, all right? Now that means that electrical energy that's around there in the electric field is tied to the actual charge it's creating it. It's bound to it. And those are called virtual photons. And don't worry about that because that's getting into quantum electrodynamics and stuff beyond this course. But just realize that that electric field is tied to the charge. Similarly, the magnetic field around an inductor is tied to the current creating it. If you take an inductor with a large current going through it, and you take a resistor and just stick it right across there, all that magnetic energy will basically cause current to pass through the resistor. You'll get I squared times R heating, and the integral of I squared R through that resistor dt would be the total amount of electrostatic energy in the inductor, 1/2 Li squared. Just trust me on this one. So that H field's tied to the current creating it. What we're talking about is something that's launched. When you have accelerated charge, and accelerated charge can be created by just taking a wire and driving it with a voltage, 100 cosine, or really just say 10 times cosine of 1,000 pi t. That will cause an acceleration of charge. And when you have an acceleration of charge, it launches an electromagnetic field. And what I'm showing you here are contours of constant electric field from a point. Now, if you look at this, if you get very far away, say I'm over here, and that's where the charge that caused the electric field happened, then primarily the contour looks like a straight line, doesn't it? The radius of curvature is going towards infinity. Radius of curvature would be the radius of one of those contours of potentials. Time goes on, and this thing expands and expands. Pretty soon, this looks like over a smaller dimension, a straight line, doesn't it, class? Or it looks planar. And that's what we're talking about when we say plane waves. We're a long way from the source that creates it. So if we're talking about plane waves, I will tell you this, I think of ways to explain this. There are very, very definite mathematical definitions of plane waves, but the problem is you can't really appreciate what I'm talking about. Here, I'm trying to make it as simple as I can so you get a visual in your mind about what's going on. So if we're talking about a plane wave, first thing is that the electric field, if it's propagating from this plane is moving that way. It's moving only in one direction. Do you follow me on that? And I'm going to assume for a plane wave, for now, that they're moving in the z direction. gonna go a step further, and I'm gonna say the electric field that we're talking about has only one component, and it only has an EX. So we're saying that we're gonna have an electric field with only an X component propagating in only the Z direction. Got me on this one, class? I know it seems like a big bunch of assumptions, but this is actually quite reasonable for anything. If you have an antenna a couple of miles away and you're talking about what's happening inside this room from that antenna, from a broadcast, this is very reasonable. Now, here's the other thing. There's no variation. If that's the Z direction, DEX DE dx is equal to DEX dy, and that's equal to 0. With a plane wave, it doesn't matter where you are. If that's Z and this is X and that's Y, where you are in terms of Y or Z or X position, the E field is the same. Got it on that, class? The assumption of a plane wave is when you're far enough away that this can be looked at as just a solid piece of really of rectangular material, and anywhere in that rectangle that's perpendicular to the direction of propagation, the electric field has the same magnitude, right? And that means the derivative of the electric field's value with respect to either X or Y is 0. Now we go into the del squared of E, and don't write this down, but let me just talk about this for a second. Del squared operations of E is actually a vector operation. If we're in Cartesian coordinates, that's equal to d squared dx squared plus d squared dy squared plus d squared dz squared operating on EX with respect to X plus, same deal, second derivative with respect to X squared plus second derivative with respect to Y squared plus second derivative with respect to Z squared operating on AY, and plus that same thing operating on EZ. Now if you look at this, that's possibly 9 derivative operators operating on 3 field quantities. That's a whole lot of stuff to keep track of. All right? So what we do is, by doing this, making sure that we have EX with respect to X and DEX with respect to Y be 0, and only an X component, we get rid of the EY component, the EZ component, and we only have a rate of change with respect to Z. So this whole del squared operator boils down to the second derivative of EX with respect to Z squared. Can you appreciate this? So we eliminate all the unnecessary complexity to try to get a visual on what's really going on. Gross is going to throw me out here in a second. So now if I have this, and I'm going to solve this equation, just let me do this for a second. So now I have del squared of E minus gamma squared of E equals 0. Are you with me? And here that del squared of E is this. So that means it's the second derivative of EX with respect to Z squared plus gamma squared EX equals 0. And the solution to that is just EX is equal to some EX0 e to the minus gamma Z AZ. And this is a plus here, plus EX0 minus e to the minus gamma, or plus gamma Z. And I want to stop there and just tell you what I'm talking about here. You remember back in transmission lines when you had V0 e to the minus gamma Z, right? Well, if this was a V, not an E, that would be a positive traveling wave right there, right? Y'all remember this back in the day? And what about this one over here? That would be a negative traveling wave, minus the direction. So this is the general solution for the E field, right there in the phasor domain for a plane wave. And I'm out of time right now, but I'm going to pick, no, that thing's way off. John, do you have 917?
Yeah, 918, yeah.
All right, but we're going to start there. I'm going to give you a few problems to do with this. And let's see, we got a test next Wednesday, is that right?
Mm-hmm.
All right, so we will get a Friday quiz. The Friday quiz won't be on that, it's going to be on all the stuff with induced EMF and magnetic circuits and things like that. All right. So just be ready for that. Any questions about this? I know this looks scary and hairy and it's like, oh, you're getting into the wacky physics. It's not that bad. This mathematics is necessary to describe it, and then you'll see, if you guys go for, I hope a bunch of you guys end up going to grad school and get PhDs and stuff like this. A lot of this stuff becomes very apparent. It's complicated, yes, but you can see the simplicity. And I want to tell you one other thing. In nature, this fascinates me all the time. The only way we find out about forces and things like that, about these equations, is through experimental measurement. What's observable? Well, we can observe electromagnetics very easily. We can observe gravity. Those are two forces, electromagnetics and gravity. There's also forces called the strong force. And if you take a look at, like, how come in the nucleus of an atom, when you have a bunch of positive charges, they don't blow apart, right? Right? Well, the nuclear hooks are holding them together are called a strong force, and it's fairly well understood too. Then there's the weak force. Have you heard of the weak force in physics? In when you talk about enormous distances, there's a force that is acting on these things, slowing things down from the rate that they should progress. That's called the weak force, if you remember, right? And the weak force also dictates what? Radioactive decay. You know? Now, all those four forces are coupled in some way. Do you know that when light goes around a planet, gravity actually bends it? Do you know that? Well, that means that the electromagnetic field, the light, right, is being affected by gravity. There's some coupling between gravity, really the force of gravity, and electromagnetics. There's also coupling between the strong force and gravity and the strong force and electromagnetics and the weak force. They're all coupled. It's called the unified field theory that Einstein was working on when he died, and everybody's still working on. And the reason is this. If you can figure that out, how everything interacts in the visible universe, then you can do some grand engineering. They call it, I mean, things that could involve deep space travel at amazing velocities, and I mean, things that are almost incomprehensible now that are part of, like, I don't know, Star Wars kind of things, or things like when Roddenberry wrote Star Trek, talk about going, what he said, warp 10 or something. It's what, 10 to the power 10 times the speed of light is the velocity to go up. Those kind of insane things that seem impossible now become at least understandable how they do it. The real problem with most of this stuff is, and I hope you guys go to grad school, it's never about the theoretical way to do something. It's always about the energy sources needed to create it and the ability to contain those energy sources. But I'm going to stop there. There's a lot more I'll tell you, but I hope you go to grad school.